Being asked to find the point of the graph of the square root function that is close to this point. So solution will start by drawing a picture to find it over here. There is the y-axis, there is the x-axis of xy, and the square root function looks something like this. Okay, and we want to find the point on this graph that is close to 3, 0. So maybe it is here, so maybe that the point right there. So D here will be this distance between our point here on the graph and 3, 0, and in order to as close as possible, we want D to be small as possible. So this point here can be written as x, y, but in this problem y is equal to the square root of x. So this point here is really x square root of x, and now we will use this distance formula. So recall the distance formula says you subtract the x, u square, then you add it, and then you subtract the y's. Okay, so here D will be the square root, so we will subtract the x, so x minus 3, so x minus 3, and that being squared plus, and then we will subtract the y's square root of x minus 0, square root of x minus 0 square. And so you see how you can generalize this. If you had any function, it does not matter what it is, you would just write this, then you would just do x minus the number they give you, and then the function minus the y value. Let's clean this up. This is D equals, if you multiply this out, you square the x, so you get x square, you multiply this and you double it's minus 6x, and then you square the 9, so the square the 3, so plus 9, then you square the square root of x, so you just get x. So D is the square root of x square minus 5x plus 9, and we are trying to make this small, right? We are trying to make this small as possible. Now the square root function is as small as possible whenever this is as small as possible. So instead of making this entire things as small as possible, we will make whatever is inside the square root and small possible. That's equivalent. So we are going to get g of x equal to x square minus 5x plus 6, and we are going to make g as small possible, right? It is trick so that you don't have to worry about the square root again. This whole things here is as small as possible whenever this term here is small possible. So we are allowed to just drop the square root and focus on making this small. All right, we will use the second derivative test. Use second derivative test. The test say that we find the critical number and we plug this into the second derivative. If we get a positive result, we are minimum. If we get a negative result, we are have maximum. We will find the critical number. So we take all the derivative and set it equal to 0. So here we get to x minus 5, right? The derivative of x square is 2x. The derivative of minus 5x is minus 5, and the derivative of 9 is 0, and we set this equal to 0. So we will add it 5, so we'll get to x equals 5. So x is equal to 5 over 2. So that is our critical number. Now to finish using the second derivative test, we have to take the second derivative, so g double prime of x, that just 2, and then we will evaluate G double prime as 5 halves, and the critical number that is still just 2, that positive. So we have a minimum. I will write at x equals 5 halves to actually find a point. Recall that our original function was the square root of x, so the final answer will, we already have the x value. We have to take the second derivative, so g double prime of x, that just 2, and then we will evaluate G double prime as 5 halves, and the critical number that is still just 2, that positive. So we have a minimum. I will write at x equals 5 halves to actually find a point. Recall that our original function was the square root of x, so the final answer will, we already have the x value, we need the value. To find the y value, you just take your critical number and plug it into your original function, and the final answer will be right here. It is the 0.5 half, square root of 5 halves, and that